So we've kind of moved on from the really math-heavy sections of stoichiometry, molar mass, balancing equations, and so forth. We're going to move into something that's a little more visual. So some people really like this because if you're a visual learner, if you can kind of imagine things in 3 dimensions, then this section actually is a lot of fun. It's all about drawing molecules. Now, before we actually start drawing them, let's just review a couple of things. Remember that a covalent bond is a shared pair of electrons. Now, it's important to note that this is a sharing of 2 electrons. So every time I talk about a single bond, that means 2 electrons are involved. Now, when we start to bond multiple atoms together, we now have a molecule, right, held together by covalent bonds. So we can go ahead and represent this. As you can see here on the left, we have a hydrogen atom, and it has one little dot next to it, and that represents an electron. In fact, we're going to represent the valence electrons using small dots. So you can see that we have one electron with that hydrogen, one electron coming in with this hydrogen. When they come together, they form a covalent bond, and that's why there's a little line in between the two. That line represents 2 electrons. So remember, 2 electrons per bond. Now, over here on the right, you can see that we have a hydrogen molecule, this time coming in again with 1 valence electron. And there's a chlorine, and the chlorine happens to have 7 valence electrons. Now remember that we can figure out how many valence electrons something has simply by looking at its location on the periodic table. Hydrogen is in column 1A, so if it's in column 1A, that means that it has 1 valence electron that we can work with. Chlorine, on the other hand, is in column 7A. Since it's in column 7A, it has 7 valence electrons. So the hydrogen and the chlorine come together, they form a covalent bond between them, and now we have a molecule, right, a hydrogen chloride molecule. So you can see that the dash, or the line in between the 2 atoms, represents a covalent bond of 2 electrons, and then we also have a couple of what we call lone pairs. So you can see in a few locations here on the chlorine that we actually have what are known as lone pairs. Alright, so a lone pair is simply an unshared pair of electrons. Now also remember that the rule of thumb for this section is going to be the octet rule, that the vast majority of atoms want to gain a full octet, or 8 valence electrons. There are some exceptions to this, and I'll go over those in a few minutes, but just remember that the vast majority of atoms want 8 electrons, which is why, if I go ahead and clear this out, you can see that by bringing in a chlorine here, with that one empty spot, the hydrogen actually fills in that empty spot. So if I were to count, I could look at this and say I have 2 electrons here, that gives me 4, that gives me 6, and then that shared pair in the bond gives me a grand total of 8 valence electrons, and that's just perfect for chlorine to have an octet. Hydrogen is one of the few exceptions to this rule. Hydrogen maxes out at 2 electrons. So notice that in every case, hydrogen always ends up with a total of 2 electrons. So here this hydrogen has 2 because of that shared pair of electrons, that bond there, and this hydrogen also has 2. And notice that we're double counting that bond there, and that's perfectly fine because it's a shared pair of electrons. Now, in order to draw molecules, we're going to use something known as Lewis structures, sometimes called electron dot structures, but these are called Lewis structures after the famous chemist G.N. Lewis, who was absolutely brilliant. In fact, he grew up in Weymouth, Massachusetts. He was nominated 35 times for the Nobel Prize because of things like the fact that he came up with the idea of Lewis acids and bases. He also basically discovered the covalent bond. So quite a few different things that G.N. Lewis did. He actually never won the Nobel Prize, even though he was nominated 35 times. He had made quite a few enemies because he wasn't terribly kind in the things that he said about other people. In fact, one of the people that he offended during a visit to UC Berkeley, where G.N. Lewis was working, Lewis showed up late to the presentation, and then when he got up to actually introduce the person, he introduced him and said, "This is so-and-so, about whom we've heard so much and from whom we have seen so little." And yet again makes another enemy. So again, very interesting character. But these are called Lewis structures, and the idea behind this is that we are going to use dots again to represent the the valence electrons, and then we're going to use single lines to represent a single bond, a double line to represent a double bond, dots to represent lone pairs, and so forth. Now remember that the most important thing here is that we are only using valence electrons. So if I'm looking at something like iodine, if I look on the periodic table, iodine has 53 electrons, right? But most of those are in the core. The only ones that are on the outside shell, the valence shell, are the valence electrons, of which there are 7 because iodine is in column 7A. So again, very important to remember, we're only looking at the valence electrons. Now, a couple of things that we should be aware of, and these probably seem pretty intuitive, but we're going to say that a single bond is when 2 atoms share 1 pair of electrons, and this is just 2 electrons, right? So we showed this earlier. Oops, back up for a second. I showed this earlier between 2 hydrogens, something like this. This could also be between, maybe a carbon and a hydrogen, right? Or 2 fluorines. And it doesn't matter whether or not there are lone pairs on some of the atoms, like in the case of fluorine, but this would be a single bond here in the middle, right, which represents 2 electrons. Now, we could also have a double bond, and in a double bond, you are going to have 4 electrons, right, 2 pairs. So this would be something like an oxygen atom. So oxygen, when it bonds to itself, will end up looking something like this, with 2 pairs of electrons in the middle. We call this a double bond, and as you can imagine, if electrons are kind of the glue that holds molecules together, a double bond has twice as many electrons as a single bond. It's going to be shorter and stronger than a single bond. Now, it's not going to be twice as strong, but it is going to definitely be stronger. Now, you can also imagine that if you can have a double bond, we can also have a triple bond. So this would be something like with nitrogen. Oops, back up again. So with nitrogen, we can actually have 3 pairs of electrons, or in other words, 6 electrons, with a couple of lone pairs here on the nitrogens, and this would be a triple bond, which is shorter and stronger than even a double bond. So I'm going to go ahead and go over the rules for drawing Lewis structures, and then I'll actually go through multiple examples so that you can kind of see how this works. Now, there are different ways to do this. Some people prefer different methods. Some people like to look at patterns, common bonding patterns and so forth, and kind of piece molecules together that way. And that works pretty well. I find that this is the easiest way for me, and seems to be the easiest for my students. So that's what I'm going to go over with you. Now, if I'm going to draw those structures, the very first thing I need to do is to count the total number of valence electrons. And remember, you can do that by looking at where the element is on the periodic table, looking at the top of the column, and looking at the Roman numeral in front of the A. So for instance, carbon is in column 4A, so it has 4 valence electrons. We're going to go ahead and add up all the valence electrons that are in the molecule, and then we're going to end up kind of divvying those out so that each of the atoms has enough, which means that they want an octet. So I always kind of think of this, and this shows how geeky I am, that it's kind of like this big atomic party, right? So you invite all these different atoms to the party. They all bring different numbers of refreshments, and then your job as the party coordinator is to kind of divvy those out and make sure everyone gets enough to eat, right? And in most cases, that means giving each atom a full octet, or 8 electrons, except for the exceptions that I'll mention in a few minutes. Now, after you've counted the total number of valence electrons, your next job is to kind of arrange the atoms. Now, there are different ways to do this. Some people will tell you that you need to look at the, least electronegative element put in the center, but we haven't learned about electronegativity yet, so that doesn't help much. Now, for this course, the basic thing that you need to do is to, just try to make it nice and symmetrical, right? We don't want anything crazy. So, just go with symmetry. Next, you're going to connect the atoms using single bonds, and it's important that those are only single bonds at this point. Then you ask yourself if you have any extra electrons. If you do, go ahead and add some lone pairs to the atoms. And I like to start with the outer atoms and then work my way in. And then also, at the very end, you need to check and see if you need more electrons. Have you given every atom an octet? If not, and you need more electrons, you can't just run to the supermarket and get more. You have to go ahead and make double or triple bonds and force those atoms to share their electrons with each other. I'm going to start with a nice easy example here with methane, CH4. And first thing I'm going to do is count the valence electrons. So carbon is in column 4A, so it brings 4 electrons to the party. Hydrogen is in column 1A, so it only brings 1. But notice that we have 4 different hydrogens. So 4 plus 4 times 1 gives me a grand total of 8 valence electrons to work with. So that's step 1. Okay. Step 2, I need to arrange the atoms and try to make these in a nice symmetrical fashion. Now, what do I mean by that? I mean, I don't want something like this with a carbon and then a hydrogen to the right of it, and then another hydrogen, and then maybe a hydrogen down here, and then maybe one kind of branching off over here. It doesn't look nice and symmetrical. Okay, and nature loves symmetry. So what I'm going to do instead is I'm going to go ahead and put the carbon in the middle, put the hydrogens around it. And by the way, carbon loves to be in the middle. I always think of C for center of attention. So, if you ever have a carbon, put it right there in the middle, and you're probably right. All right, so carbon's in the middle. We've done step 2, arrange the atoms. Next thing, we're going to go ahead and connect the atoms using single bonds. So I'm just going to go ahead and attach each of these. Now remember that each of those is a single bond, but it represents a shared pair of electrons. So we have 2 electrons. So how many have we used? Well, we've used 2, 4, 6, 8. We've used a grand total of 8 valence electrons. So we're totally out of electrons. Now we don't have any extra electrons, so the next thing we need to do is just double check. I should mark these off. Double check to see if we need more electrons. So are all of our atoms happy? Are they stable? Well, remember that I mentioned the hydrogen maxes out at 2 electrons. So you'll notice, I'm going to put this in red, that this hydrogen here has this bond here, right, which represents 2 electrons. So that hydrogen has 2 electrons, this hydrogen has 2 electrons next to it, this hydrogen has 2, and this hydrogen has 2. So each of those hydrogens has exactly 2 electrons next to it, so that's good. All right, what about the carbon in the middle? So with this carbon in the middle, it has 2, 4, 6, 8 electrons around it, right? Now notice that we're double counting those shared electrons, which is perfectly fine because they are shared. So we're counting them as though they're next to the hydrogen. We're also counting them as though they're next to the carbon. So sure enough, we have a grand total of 8 electrons around the carbon, and so this is the molecule. This would be a methane molecule, okay, written in 2 dimensions. Looking at our second example, it seems very similar, right? But this time we have carbon with 4 fluorines around it instead of 4 hydrogens. So how does that change things? Well, carbon still brings 4 electrons to the party because it's in column 4A. We have 4 fluorines. Those are in column 7A, so each of those brings a total of 7 electrons, which gives us a grand total of 32 valence electrons that we need to work with here. All right, so that's step 1. What about step 2? We need to arrange the atoms. Just like before, I'm going to go ahead and put carbon in the middle, and I'm going to arrange my 4 fluorines around the center of that carbon. All right, easy enough. I've arranged the atoms. Next, I'm going to go ahead and connect the atoms using single bonds. So I'm going to put a single bond between each carbon, or between the carbon and each fluorine. Right, now notice that I've just used 2, 4, 6, 8 electrons. I still have 24 more electrons to work with, right? So my single bonds are done. Now what I'm going to do is I move on to step 4 and I ask myself, do I have any extra electrons? Well, yeah, I do. I have quite a few. So I'm going to start adding lone pairs. Let's see. Onto each of the fluorines. Alright, I apologize if my little electrons don't always look perfect here. 2, 4, 6 around that fluorine, and then 2, 4, well, let's see, 6. So notice that what I'm doing is I'm giving each fluorine a total of 8 electrons around it, right? So 3 lone pairs giving it 6, and then also the 2 that are in that bond. So by doing this, I can actually fill up the octet on each, on each of my fluorines here. So if I go ahead and count my electrons, you can see, I'm actually going to do this in a different color just to illustrate. Okay, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've used exactly 32 electrons, which is perfect. I've used them all up, which is wonderful. Now, I don't have any, extra electrons, right? So that means that I'm done with step 4. Do I need more electrons? Well, let's check. This fluorine here happens to have a grand total of 8 electrons around it. This one has 8, this one has 8, and this one has 8. And the carbon in the center has 2, 4, 6, 8 around it. So everybody's happy. I don't need any more electrons. All right, so that is our structure for a carbon with 4 fluorines around it. Let's go ahead and try one that's just a little bit trickier. This time we have carbon dioxide, CO2. So carbon has 4 valence electrons. Oxygen, well, we have 2 oxygens, and each one of those brings 6 electrons with it, giving us a grand total of 16 electrons to work with. All right, now, which atom do we want in the center? Well, probably carbon, right? I mentioned carbon loves to be in the middle, and so yet again it is. I put the 2 oxygens around it. Notice that I put them on the left and the right. You could have put them on the top and the bottom. It doesn't matter. These are, really three-dimensional molecules, so you could rotate these any direction you want. I just put them on the left and right because it's easy. All right, I'm going to attach them via single bonds to that carbon. And now, on step 4, I do have a lot of extra electrons, right? I've used 2, 4, so I still have 12 electrons. So, I'm going to go ahead and start filling up the octets around each of my oxygens. All right, I've used 2, 4, 6, 8, 10, 12, 14, 16. I've used up all 16 of my electrons. Now you might be tempted to think that you're done, but we're not quite done, right? We don't have any extra electrons, but in step 5 it asks, do you need more electrons? And in fact we do, because notice that this oxygen on the left has 2, 4, 6, 8 electrons around it. The one on the right also has 8. But the carbon in the middle only has a grand total of 4 electrons around it, right? 2 from this bond and 2 from this bond. So the carbon is kind of like that guy at the party that's starving. He's like, dude, I want some more taquitos or something. So we need to somehow force the oxygens to pass over some of those. So we're going to force the oxygen to make a double bond. So I'm going to go ahead and remove this pair of electrons on the bottom, and I'm going to actually put that in as a double bond here, right? So I've just shifted that over. Now notice that this oxygen still has 2, 4, 6, 8 electrons around it. So the oxygen is still perfectly happy. Is the carbon happy? Well, not quite, because it only has 2, 4, 6, so it's still not quite enough. So what I'm going to do is I'm actually going to go ahead and force the oxygen on the left to share a pair of electrons. Now I could go ahead and remove any pair. I could remove this pair over here. It's totally fine, it doesn't matter, because remember these are three-dimensional. And now notice again that I've still used 2, 4, 6, 8, 10, 12, 14, 16 electrons. So I've used the appropriate number of electrons. And I've also made sure that this oxygen has 2, 4, 6, 8. This one has 2, 4, 6, 8. And if we count the carbon in the middle, it has 2, 4, 6, 8. So everybody has exactly 8 electrons, has an octet, which is exactly what we want for a nice stable molecule. Now let's try drawing PCl3, phosphorus trichloride. So phosphorus is in the same column as nitrogen. It's in column 5A. So that has 5 valence electrons. We have 3 chlorines. Each of those brings 7 electrons with it. So let's see, that's 21. That's a total of 26 valence electrons that we have to work with. And again, remember that we are only counting valence electrons. If you look at phosphorus, it actually has 15 electrons, but only 5 of those are in the outermost energy level, and those are the ones that we care about. All right, so our next step is to go ahead and draw this. I'm going to put phosphorus in the middle and put the 3 chlorines around it. I put them on the left, right, and the bottom. I could have put one on the top. It doesn't matter, okay? So don't get caught up on something like that. I'm going to attach them via single bonds to that central phosphorus. And now I need to count my electrons. I've used 2, 4, 6, so I still have 20 more electrons. I'm going to go ahead and start adding lone pairs, okay? So if I add these to each of the chlorines in order to give the chlorines a full octet, so I fill up each octet and then move on. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used 24 electrons. I can't give any more to chlorine, so I'm going to go ahead and give a lone pair to the phosphorus here. So notice 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I've used exactly 26 electrons, which is perfect because that's exactly how many I have. And now I just need to double check. This chlorine has 8, this chlorine has 8, this chlorine has 8, and the phosphorus has 2, 4, 6, 8 around it. So it's also nice and happy, perfectly stable, right? So that is my PCl3 molecule. Let's go ahead and try one more, all right? So this is hydrogen cyanide gas. Happens to smell like almonds, or I should say almonds happen to smell like hydrogen cyanide gas, because almonds actually do contain low levels of cyanide. So if you ever walk into a lab and it happens to smell like someone's roasting almonds in there, you should actually run away quickly. This happened once at the University of Utah when I was there. Someone accidentally poured cyanide salt into a waste container that had acid in it, produced some hydrogen cyanide gas, and they had to evacuate the building. Luckily no one was hurt. So anyway, let's go ahead and draw this thing out. Count my valence electrons. So I have 1 for hydrogen, 4 for carbon, 5 for the nitrogen, giving me a grand total of 10 electrons to work with. Now, how should I draw this? Because it's not going to be symmetrical either way. Well, it's written HCN, which should be a tip-off that it should be drawn HCN and not HNC or anything like that. So I'm going to draw HCN. I'm going to attach the hydrogen and the nitrogen to that central carbon using single bonds. I still have, let's see, a grand total of 6 more electrons to work with. I'm going to go ahead and start adding these as lone pairs. Now, can I add them as lone pairs over here on the hydrogen? No, because remember that hydrogen maxes out at 2 electrons, right? It can't handle any more than that. So going back to the analogy of having like this atomic party, hydrogen's like the little kid at the party. If you try to force feed him extra electrons, you get nothing but like electron vomit all over in your carpet. Nobody wants that. So I'm going to go ahead and remove those electrons from the hydrogen. Instead, I'm going to go ahead and put those on the nitrogen. So I've used 2, 4, 6, 8, 10. I've used all 10 of my electrons. Now am I done? Well, let's check. The hydrogen has 2 electrons around it, so the hydrogen is perfectly happy, right? The nitrogen has 2, 4, 6, 8 electrons around it, so the nitrogen's perfectly happy. But if we check that carbon in the middle, it only has 4. So the carbon's not happy. It wants an octet. So what can we do? Well, we can force the nitrogen to form a double bond, right? There's nothing we can do with the hydrogen because the hydrogen made a single bond. That's all it can do. But if I go ahead and pull off a lone pair of electrons from the nitrogen and force it to share that with the carbon, the nitrogen still has 8 electrons around it, so it's still happy. The carbon's now at 6, which is good, but not quite good enough. So I'm going to pull off another pair of electrons from the nitrogen and form a triple bond. And so notice that we've still used 2, 4, 6, 8, 10 electrons, so we've used the appropriate number of electrons. But now the hydrogen's happy with 2, the nitrogen on the right has 8, and the carbon in the middle has 2, 4, 6, 8. So all of our atoms have an octet, or in the case of hydrogen has a duet, and so they're all nice and stable now. So hopefully you feel pretty comfortable with drawing some neutral molecules. Now let's try throwing a curveball at you. We're going to actually draw some polyatomic ions. Now remember, polyatomic ions is simply a group of atoms that has an overall charge. So something like the ammonium ion with a +1 charge, or a phosphate ion with a -3 charge. Turns out this is the exact same procedure as before with a couple of changes. Okay, if the polyatomic ion happens to have a negative charge, we're going to add 1 electron. And if it happens to have a positive charge, we're going to subtract 1 electron. Right? Now this may seem counterintuitive because you think, oh, a positive charge, that's plus, right? So I should add electrons. But no, remember that electrons are negative. So by adding an electron, you're actually adding a negative charge. So let me show you this in action. If I'm drawing the ammonium ion, NH4+, I can add, let's see, 5 electrons, valence electrons for the nitrogen, 4 times 1 for the hydrogen, and then I'm going to go ahead and subtract 1 electron due to that positive charge that's on the ammonium ion. Alright, that gives me a grand total of 8 electrons to work with. I can go ahead and, just like before, arrange this in a nice symmetrical pattern with the hydrogens surrounding the nitrogen, attach the hydrogens to that nitrogen using single bonds, and if I count these up, it looks like I have 2, 4, 6, 8. I've just used all 8 of my electrons. Alright, and let's go ahead and make sure that everybody's happy. This hydrogen has 2, this has 2, this has 2, this has 2, so those are all good. And then what about the nitrogen in the middle? It has 2, 4, 6, 8 around it, so it's a nice stable atom as well with a full octet. Now the last step is that it's customary that when you're writing an ion or drawing an ion like this, to put it in square brackets and to go ahead and put the charge on the outside. So I'm going to go ahead and just put a plus charge on the outside of the square brackets just to indicate what that is. Now let's go ahead and try the same thing with a nitrate ion. So nitrogen has 5 valence electrons, 3 times 6 for the oxygen, and I'm going to add 1 more due to that negative charge. That gives me 18, 19, 24 electrons to work with. Alright, which one goes in the middle? Probably the nitrogen. That would make the most sense. Go ahead and put the oxygens around it. Attach them with single bonds. Now notice that I've only used 6 electrons. I still have 18 more. So I'm going to add them in. Let's see, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used a grand total of 24 electrons. So am I done? Well, let's go ahead and double check. This oxygen on the left has 8, the one on the right has 8, the one on the bottom has 8. So the oxygens are great. The nitrogen, however, only has 6 valence electrons around it, not quite enough. So that means I need to go ahead and form a double bond. And I could form this with any of the oxygens. Let's say I go ahead and use this lone pair of electrons, force that to become a double bond. Notice that I've still used exactly 24 electrons. Each of the oxygens still has 8 if you count them up, and the nitrogen now has 8 electrons as well. Now I go ahead and put the square brackets and my little charge out there, and now I have a nice stable nitrate polyatomic ion. So the exact same procedure as before, just remembering to add or subtract the appropriate number of electrons depending on what kind of charge you have. So now that we've gone through drawing normal neutral molecules and polyatomic ions, let me go ahead and mention a few of the exceptions to the octet rule, because remember that the vast majority of atoms want a full octet, or 8 electrons. But there are a couple of exceptions. So I've already mentioned hydrogen, which can only handle 2 electrons. Beryllium typically handles 4 electrons, and boron will often handle only 6. So let me go ahead and show you what one of these would look like. So what would happen is I'd go ahead and give you a molecule like BH3, and I'd ask you to draw that out. And so first you would count your valence electrons. So boron only has 3 valence electrons, 3 times 1 for the hydrogen, giving me a grand total of 6 electrons. So at this point, you should probably say, wait a minute, 6 electrons, I cannot make an octet using only 6 electrons, so something fishy must be going on here. And you'd be right, but then you'd probably say, oh yeah, boron's one of the those weird exceptions, right? And you'd be right. So in this case, I'm going to put the boron in the middle, put the hydrogens around it, attach them with single bonds, and notice that I've already used all 6 of my electrons. Okay, I can't make any double bonds, I can't make triple bonds, I can't do anything with this because I've used all my electrons. So I just check to see how everyone's doing. The hydrogen has 2. This hydrogen and this hydrogen both have 2 apiece, which is perfect. And the boron in the middle has 6, which is okay because remember that boron is perfectly happy with only 6. This is kind of like you go to the party and someone's on a diet and they're like, oh, no guacamole for me, that's okay. I'm happy. You know, just having this like rice cake or something. So these are kind of the weird ones that don't really need the full amount. Now, another exception that you might see occasionally are what are known as odd electron species. As the name implies, they have an odd number of electrons, so it should be pretty obvious when you see one of these because you'll get an odd number of electrons. So let me show you what that would look like. In this case, we have NO, okay, my daughter's favorite word. So nitrogen monoxide. And when we do this, we add up 5 valence electrons for the nitrogen, 6 for the oxygen, and notice that that gives us 11 valence electrons to work with. So again, right off the bat, you should say, something's fishy here because I only have 11 electrons. That's not an even number. How can I put pairs of electrons with this? Well, it's okay. So let's go ahead and just draw the nitrogen and the oxygen next to each other, attach them with a single bond, and then let's go ahead and just start filling up the electrons here. So that's 8, that's 10, that's 11. So I've used 11 electrons. That's all that I have. Now oxygen has a grand total of 8 around it, so it's perfectly happy. But notice that nitrogen only has 2, 4, 5. Not a good position to be in, right? So what I'm going to do is just like before, I'm going to go ahead and yank off a pair of these, this lone pair here, and I'm actually going to force that oxygen to share that pair of electrons with the nitrogen. So notice that I've still used 2, 4, 6, 8, 10, 11 electrons. So I've used the appropriate number. And I've still made sure that oxygen has 8, so it still has an octet. Nitrogen has 2, 4, 6, 7, right? That's as close as I can get to 8 without going over. So that's the actual structure of this. Now you can imagine that this isn't going to be terribly stable, right? Because nitrogen really wants an extra electron. So this is what's known as a free radical. You've probably seen this on skincare commercials where they say, oh, for only $95 you can buy this little tube of skin cream that helps to fight fine lines and wrinkles and free radicals and terrorists and all this other stuff. And so free radicals are these kind of things that have this unpaired electron, and these are incredibly unstable and will react with anything, including like your DNA, which can then lead to cancer. Now, one problem with this, or one kind of question you might have, is why did we put that kind of weird electron, that odd electron on the nitrogen? Couldn't we have done something like this and drawn the odd electron on the oxygen? Well, yeah, we could. And it turns out that when we get to higher levels of chemistry, we do something called formal charges that allows us to determine which structure is better. And it turns out that this structure is better. For right now, the easiest thing to remember is that nitrogen is the one that brought an odd number of electrons to the party. So I'm going to go ahead and make sure that nitrogen has to get stuck with that weird odd number of electrons. And so this would be the better structure for you to draw. So we've gone over a couple of exceptions to the octet rule, typically that involve what are known as incomplete octets. So now we're going to talk about something known as expanded octets. So as the name implies, these are atoms that can actually go beyond 8 electrons. Now, how is this possible? Well, it turns out that if you go back to the section on electrons, we found out that starting in the principal energy level of n equals 3, that we actually have d electrons, right? Or d orbitals for electrons. And so elements in row 3 and below actually have empty d orbitals. So we have horizontal row 1, 2, 3. So anything in this row 3 and below can go ahead and expand its octet if necessary. Now, this doesn't mean that they always will. It just means that they can if necessary. This is kind of like me at a party, right? I go to a party, and if there's just enough food to go around, I'm not going to be a pig and take too much. But if they're like, hey, there's extra pizza here, dude, I'll totally eat it. So same type of thing is going to happen here. The most common ones that you'll see are probably sulfur, phosphorus, chlorine, iodine, and so forth, can actually expand their octet. So let me go ahead and show you an example of this in action. Alright, so this here is sulfur hexafluoride, which is actually a really fun molecule. If you have some time, you should go on YouTube and search for sulfur hexafluoride, and you'll find out that there's like a Mythbusters clip about this and a few others. So helium makes your voice go very, very high because helium is less dense than air, and so when you inhale it, sound waves travel faster through it, and so it makes you sound like Mickey Mouse. Now, sulfur hexafluoride, on the other hand, is much denser than air. So if you inhale a bunch of sulfur hexafluoride, then when you speak, it actually kind of sounds like you're Darth Vader. You have this really, really low voice. And so lots of fun. Anyway, so let's go ahead and draw this thing out and see what it should look like. Well, sulfur is in column 6A, so it brings 6 electrons with it. We have 6 fluorines. Each of those brings 7 electrons, giving us a grand total of 48 electrons to work with. So that's a lot of electrons. I'm going to go ahead and put sulfur in the middle, surrounded by 6 fluorines. I'm going to connect each of those fluorines to that central sulfur. It's a little lopsided, that's okay. And now I'm going to go ahead and add in lone pairs. Oops. Sorry, the electron's a little smudgy looking. Let me just back those up. All right, try that again. Much better. So if I fill in each of these octets around the fluorines, then in about 3 weeks we should have a molecule. It's hard to write so small to give myself enough space to do this. Oops. Now, while you're watching me struggle to add all these dots, if you count them up, you'll actually see that we've given fluorine a grand total, or given this molecule a grand total of 48 electrons. So we've used the proper number. You'll also notice that each of the fluorines has a nice octet with 8 electrons around it, just like normal, so nothing special there. But what is kind of weird about this is that sulfur actually has 2, 4, 6, 8, 10, 12 electrons around it. So this has far too many electrons, but it's okay because sulfur is in horizontal row 3. So anything in horizontal row 3 and below can go ahead and expand its octet. Now, remember that I mentioned that sulfur doesn't have to expand its octet. So let me just show you. For instance, in hydrogen sulfide, which is rotten egg smell, highly toxic actually, you'll notice that sulfur has a nice normal octet, 8 electrons, right? So sulfur and other elements in row 3 and below, if there's just enough electrons for everyone to have 8, they'll just take their fill. But if there's extra electrons, like in the case of sulfur hexafluoride, then sulfur is more than happy to shuttle some of those extra electrons into its empty d orbitals. All right, one last curveball I could throw at you would be what are known as resonance structures. So it turns out that occasionally, when you're drawing a molecule, you can actually draw more than one valid Lewis structure for it. So more than one structure that completely follows all of the rules, that doesn't break any crazy, rules for this. But if you can do that, then we say that it actually exhibits resonance. All right, and the actual molecule is a hybrid of all those possible Lewis structures, right? So you know what a hybrid is? It's kind of like a hybrid car, gas and electric, or a Liger, which is pretty much my favorite animal, bred for its skills in magic. So anyway, let me show you an example of this in action. So this would be ozone, O3. And if I go ahead and start drawing this, first thing I need to do, just like always, is to count my valence electrons. So I have 3 times 6, because oxygen's in column 6A, giving me 18 electrons to work with. Now I'm going to go ahead and just put all of those oxygens in a nice little row, connect them with single bonds, and then I can start filling out the octets. I've used 4 electrons so far, so that would be 6, 8, 10, 12. Oh, actually, I like to go from the outer atoms and move in. So I've used 2, 4, 6, 8, 10, 12, 14, 16, and I still have 2 more, so I'm going to go ahead and put that extra pair on that central oxygen. Now, how am I doing? Well, the 2 outer oxygens are perfectly happy because they each have 8 electrons, but the oxygen in the center only has 6, so this is a problem. So I can go ahead and make a double bond, just like I've done before. The question is, do I pull it from the oxygen on the left or the oxygen on the right? Well, I'm going to pull it from the oxygen on the left, make a double bond. Now that's perfectly valid, but it also would have been perfectly valid to draw the molecule with the oxygen in the other, or the double bond on the other oxygen. I can't talk and draw at the same time. Alright, so I could have drawn this molecule, and notice that that's also perfectly valid. It doesn't break any of the rules for Lewis structures, uses the appropriate number of valence electrons and so forth. And so I'm going to draw a double-headed arrow between this. This is what are known as resonance structures. And it used to be thought that the structure kind of resonated between the two, that double bond would kind of bounce back and forth between those two. And it's actually not true. They found that in actuality, you don't have a single and a double bond. You have 2 identical bonds that are have about the strength and the length of a 1.5 bond. And so it's kind of weird. And that's one of the few failings of Lewis structure, that it doesn't give an appropriate structure for things that exhibit resonance. You actually have to draw multiple structures and then hybridize them together. Now, other molecules that exhibit resonance, you'll notice that we earlier drew the nitrate ion, NO3, with a negative charge. If you go back in and look at that, you would see that we actually had 3 different oxygens, and we needed to pull off a lone pair and turn it into a double bond. And I think we did it from the oxygen on the left, it could have been from the one on the right, or it could have been from the one in the center. And so it actually have 3 different resonance structures, and the true molecule would be a hybrid of those 3. Now at this point, or by this point, hopefully you've recognized that it's important that we can actually visualize these molecules, right? But so far we've only been writing them in 2 dimensions, and so it's still kind of hard to visualize these as 3-dimensional objects moving in space. So I'm going to go ahead and show you something kind of fun. And what I'm going to do is have a deck of cards here, and I'm going to go ahead and, if you were here, I would go ahead and just start flipping through the deck, and you would tell me whenever you want me to stop. All right, so stop there. All right, perfect. I would go ahead and show you this card, all right, and put it back in the deck. Now, I'm going to mix these up, and I'm actually going to do something known as a Pharaoh shuffle. This is actually the most precise shuffle known to man. In fact, if you can do a perfect Pharaoh shuffle 8 times in a row, the cards will actually go back into their original sequence. Now, I can't even do a single perfect Pharaoh shuffle, so it doesn't matter. But what I can do is I can make this little paintbrush thing. We can actually start painting with the cards themselves. Hopefully you can see this okay. But you can see that we actually have what appears to be the Mona Lisa. Keep painting with these cards here. I'm just going to scoot these over a little bit. You can see I'm not much of a Da Vinci here. And it appears that the Mona Lisa happens to be holding your card, which is the 5 of diamonds, right? And so in this case, you can see that I was able to kind of visualize your card into this two-dimensional painting. But what we're going to do now is actually take this into 3 dimensions. All right, so we're back. Let's see. So we're now taking this into 3 dimensions. We're going to talk about something known as molecular geometry. We're going to describe the shapes of these molecules in 3D in geometric terms, and we're also going to use what are called bond angles to describe the angles that are formed between the atoms themselves. So are they 180 degrees apart and so forth. In order to do this, we're going to use a theory known as VSEPR, VSEPR, valence shell electron pair repulsion theory, which sounds really fancy, but it basically just means that electrons are negative, right? And so electrons want to be as far apart from each other as possible due to those repulsive forces. So our job is to kind of separate those electron groups as far apart as physically possible. We can do this by forming different shapes. So the first and the easiest would be a linear geometry. So notice that if we have this BeCl2 or a CO2 molecule here, we have a central atom, like our beryllium atom, in the middle here. I'm actually going to go ahead and label these for a second. And then we have chlorines on either side. Now these chlorines happen to have lone pairs on them, but that doesn't matter, okay? All that we really care about is what's happening around that central atom. Well, in this case, the 2 chlorine atoms are trying to get as far apart as possible. So you'll notice that the bond angle between those 2 chlorines is actually 180 degrees, so they're on exact opposite sides of each other. Now, we could have done the exact same thing using carbon dioxide, in which case you'd have a double bond in either case, but it does not matter. Again, it's the exact same thing as before, okay? The bond angle would be 180 degrees, and we would say that this is a linear molecule. Oops, I gave myself too many electrons around there. All right, so it would look something like this. All right, so again, it doesn't matter whether we have single or double bonds. All that we care about is that we have 2 groups of electrons. In this case, 2 double bonds that are on opposite sides of each other. Bond angle of 180 degrees. Now what if we have 3 groups there? Well, in this case we'd have something known as a trigonal planar geometry. So in this case we have a boron in the center. We actually drew this out earlier. We have hydrogens on kind of the sides, and then these groups are trying to get as far apart from each other as possible. All right, and if you remember your geometry, the farthest apart that these things can be would be to go to the corners of a triangle, and that would be 120 degrees apart. So all of those angles are identical. They're all 120 degrees. Okay, trigonal planar geometry. Now things get a little trickier once we hit 4 electron groups around that central atom. So in the case of methane shown here on the left, CH4, it looks like that this is a flat molecule with bond angles of about 90 degrees, right? But it turns out that this isn't true, because if we're thinking in 3 dimensions, we would have our carbon in the middle, our hydrogens around it, and these hydrogens could actually go to the corners of a tetrahedron. Okay, you can kind of think of this as like a music stand with the tripod legs and then the music stand portion kind of sticking up out of the top, right, up here. If you are into D&D, this is a D4. I know you all are. So anyway, if you remember your geometry, 3D geometry for this, bond angles here are 109.5 degrees. Kind of sounds like a, I don't know, like a cheesy, radio station. Like, you're listening to Smooth and Relaxing 109.5, the tetrahedral station. So this is tetrahedral geometry. Now, because it's hard for us to visualize this 3D tetrahedral molecule in 2 dimensions, you'll see it drawn different ways. Sometimes, when we're being lazy, we might just draw it like this, where it's just a flat molecule. However, if we want to really show the 3-dimensional shape of this tetrahedron, you'll see something like this here in the center. Now, if it's a solid line, then that represents that or indicates that the atom is in the plane of the paper or the board here. All right, if it's a solid wedge, then that should tell you, or try to indicate to you, that it's coming out at you, right? So this hydrogen here is actually coming out of the screen at you. And then if you have a kind of a hatch mark line, then that's supposed to represent that that atom is moving back away from you. So in this case, that hydrogen's moving away from you. This is especially important when you get into organic chemistry and you're drawing these big 3-dimensional molecules, when you're talking about enzymes and the active site and so forth. This could be very important. And so often computer simulations are used to kind of visualize the actual 3D shape of the enzyme and the active site and so forth. Now, let's keep moving on. And now that we have seen the tetrahedral geometry, previously we had a carbon with 4 hydrogens around it. But in the case of back up one second. In the case of ammonia here, you can see that we actually have 3 hydrogens and then 1 lone pair. So it's like our nitrogens here. We have 3 hydrogens around it, and then we have a big lone pair up on top of it, right? And so the electrons still go to the corners of a tetrahedron, right? And so the bond angle is still approximately 109.5. The difference is, though, that this set of lone pairs is invisible, right? And so you can't see that, but it still takes up space because it's still negatively charged and it still repels all of these other electrons that are trapped within those bonds. And so the bond angle is actually a little bit less than 109.5. In nitrogen, I believe it's about 107, but approximately 109.5, because it's really actually kind of squeezing in those 3 hydrogens on the bottom, kind of like collapsing that tripod just a little bit, because this lone pair really takes up extra space because it's not confined within a bond. Now, what if we had something like a water molecule? Okay, and with a water molecule, we have an oxygen in the middle. We have 2 hydrogens out here, and then we have these 2 lone pairs, right? Okay, and so remember that those lone pairs are invisible. You can't see them, but they still take up space, and so they still force these hydrogens away from the lone pairs. The bond angle in this case I think is about 104.7, but approximately 109.5, a little less than that, due to the kind of that squeezing effect of those lone pairs up there. Now, this is called a bent geometry. The previous one was called a trigonal pyramidal geometry because it kind of looks like a pyramid with a triangular base. This one's bent, which is why water molecules are not linear. They're not straight across as we typically draw here, where it looks like the hydrogens are straight across from each other. It doesn't actually work that way. In fact, that's why water molecules are always drawn as kind of this shape like this. In fact, one of my proudest moments, parenting moments, was a couple years back. I was feeding dinner to my kids, and we used to get the dinosaur chicken nuggets from Costco, and so I'd build like a little thing with barbecue sauce for a tar pit and little broccoli florets for trees, and then the dinosaurs would like drown in the barbecue sauce and so forth. And one day Costco didn't actually have the dinosaur chicken nuggets, and so instead I had to get the lame Mickey Mouse chicken nuggets. So I brought it home and I cooked them up, and I handed them out to my kids, and my oldest daughter, who was about 5 at the time, said, "Oh, what happened to all the dinosaurs?" And I said, "Well, they didn't have them at Costco. Instead, they just had these." And she said, "Well, at least they look like water molecules." And it brought a little tear to my eye because I was so proud that she thought they were water molecules and not Mickey Mouse. So what does all of this mean? Well, this means that if I were to, give you a molecule, something like NH3, and you were to draw this, so I'm just going to quickly draw this out. You would draw the molecule, and then your job would be to figure out what's the molecular geometry. So in order to do this, once you've drawn the Lewis dot structure, you'd look at the central atom, in this case the nitrogen, and you would say, okay, this nitrogen has 1, 2, 3 atoms around it. So in this column of the table, you see that it has 3 atoms around it, and it has 1 lone pair. And notice that it's lone pairs on the central atom. Okay, we only care about what's on the central atom. We don't care if there's lone pairs on those outer atoms. It has no effect. So 1 lone pair, which tells us that the shape is trigonal pyramidal with a bond angle of approximately 109.5. All right, if I gave you a molecule like, let's say I gave you CO2, and you drew this molecule, oops, all right, so that's our molecule there. And again, what you would do is you would look at the central atom, in this case carbon, and you would say, you know what, this carbon has 1, 2 atoms bonded to it, and it has 0 lone pairs on the carbon itself. There are plenty of lone pairs on the oxygens, but 0 lone pairs on the central atom. Therefore, it's a linear molecule with a bond angle of 180 degrees. So I'd recommend having access to this table. There's also, a table like this in every chemistry book known to man. But just kind of be aware of this so that when you draw a molecule, you can figure out what the shape is going to be. Now the next thing is that we've been talking about these and mentioning that these are covalent bonds, right? A sharing of electrons. But unfortunately, sharing is not always equal, right? It's like when I used to bring home a toy for my 2 girls, and I'd tell them, oh, you need to share it. But guess who would get to share it more often, right? The older one, because she's bigger and meaner and fights dirty, and so she could take it and she could have access to it more often. The same type of thing happens when we are sharing electrons in a bond, right? So, for instance, in this hydrogen-fluorine single bond here, and there are lone pairs on the fluorine, but that doesn't matter right now, but this pair is being shared. But fluorine is stronger, right? It has what's called a higher electronegativity, and so it ends up pulling on the electrons. So the electrons spend most of their time hanging out with the fluorine. Now remember that electrons are negative, right? And so that gives the fluorine what we call a partial negative. That's what this symbol is, a lowercase Greek letter delta, a delta minus, a slight negative charge on this end of the molecule. Hydrogen's kind of left out in the cold, which means it ends up with a slight positive, or a delta plus. All right, another way to represent this would be to actually draw an arrow pointing towards where the electrons are going. So the electrons are getting pulled over to the right-hand side, so my arrow is going to the right, and then I go ahead and put a little plus sign on the other end of my arrow to indicate that I have a slight positive charge on that hydrogen end of the molecule. And this is what we call a dipole, because there are 2 poles, right, like a north and a south pole, a positive and a negative pole to this molecule. So this is an unequal sharing of electrons. How do we know which atoms are stronger or have a higher electronegativity? Well, there's a table for it. All right, so this is just a simplified table. It doesn't have any of the noble gases, because remember that those don't like to form bonds anyway, so they don't have a good electronegativity, or pretty much have 0 electronegativity. It also doesn't have the transition metals, because those aren't terribly common for what we're dealing with. So you can see here that something like fluorine over on the top right hand side has an extremely high electronegativity, a 4.0, perfect 4.0, the highest electronegativity we have. Down in the bottom left we have cesium, which is way down at 0.7, a very, very low electronegativity. So if we were to have a bond between a cesium and a fluorine, the electrons would get pulled straight to the fluorine and leave the cesium out in the cold. Now what we really need to do here is we need to actually look at the difference in electronegativity, okay, between two atoms, and that will define what kind of bond we have. So let me give you an example of this. All right, turns out that what if we had two carbon atoms bonded to each other, right? So two carbon atoms. Well, in this case, they have the same electronegativity, right? If we go back a slide, we can actually check this out. So you can see that the electronegativity for carbon is 2.5. All right, so 2.5 minus 2.5 comes out to 0, right? Which means that the electronegativity difference is less than 0.5. So we have what's known as a nonpolar covalent bond, which means that the electrons are equally shared, or at least so closely that it doesn't make a difference. So for instance, carbon and hydrogen, 2.5 minus 2.1 gives me a difference of 0.4. So there is a slight difference in electronegativity, but it's still less than 0.5, so that would be a nonpolar covalent bond. Now what about something like, that's kind of in the middle there, where the difference is between 0.5 and 1.9? Then we have a polar covalent. It's covalent, so it's still a sharing, but it's polar, which means that it's an unequal sharing of electrons. So the electrons are getting pulled towards one atom or the other. So this would be something like, let's back up for a second, something like fluorine and carbon, right? So 4.0 minus 2.5 would be a difference of 1.5. So if we go back to our table here, you can see that a difference of 1.5 is a polar covalent bond. And then the last type of bond would be if the difference is greater than 1.9. So in that case, the difference is so large that in this tug of war, one atom actually rips away the electron from the other, in which case it's not even a sharing anymore, it's actually a transfer of electrons. And remember that a transfer of electrons is defined as an ionic bond. So let's go ahead and take a look at a few of these, okay? So carbon paired up with a carbon, well, here's carbon right here, 2.5. So 2.5 minus 2.5 equals 0. So what kind of bond do we have? Well, the table tells us that that's a nonpolar covalent bond. Okay? Now, notice that I actually went through the effort of subtracting 2.5 from 2.5, but anytime you have two identical atoms, obviously it's going to be a difference of 0, right? It's kind of like having twins and they're having this tug of war. If they're both equal in strength, the rope's not going to go anywhere. Now, what about carbon versus hydrogen? Carbon is 2.5, hydrogen is 2.1, difference of 0.4. If you look at that table on the last slide, that also is a nonpolar covalent bond. Now what about oxygen versus hydrogen? Oxygen's a 3.5, hydrogen's a 2.1, so that's a difference of 1.4. So that's actually what's known as a polar covalent, right? So it's still a sharing, but it's not an equal sharing. All right, let's go ahead and try a different color just for variety. Let's see, sodium and chlorine. So chlorine is a 3.0. Sodium, here's sodium right there, is a 0.9 for a difference of 2.1. So 2.1 is such a large difference that we actually have an ionic bond at this point. So that it's actually a transfer of electrons. Now notice one thing. In this case, I actually wrote the value for the chlorine first and then subtracted the sodium from it. Now, there's a reason for that. We always want a positive value for our difference in electronegativity. So you never want a negative value. So always take the larger number and subtract the smaller number from it. All right, what about phosphorus and sulfur? Well, let's see, sulfur is a 2.5. So that's the larger value. The smaller value is 2.1. So that would be a difference of 0.4, which is a nonpolar covalent bond yet again. What about lithium and nitrogen? So lithium is way over here at a 1.0, nitrogen's a 3.0. 3.0 minus 1.0 is a 2.0, which is an ionic bond as well, right? So a complete transfer of electrons. And then carbon and oxygen would be the last one. We have a 3.5 minus a 2.5, which means that we have a difference of 1.0. So that would be a polar covalent bond. So a sharing, but not an equal sharing. So up to this point, I kind of gave you just a rule of thumb, which basically said that an ionic bond is going to be anything that involves a metal from the left-hand side of the periodic table and a non-metal from the right-hand side. But if we really look at that, the reason behind this, or the reason that that rule of thumb works, is that the non-metals over here on the far right-hand side typically have very high electronegativities. The metals over here on the left-hand side typically have very low electronegativities. So when you have a bond between them, the difference is so large that the difference in electronegativity is greater than 1.9, which is considered a transfer of electrons, an ionic bond. And then I also mentioned that a covalent bond typically occurs between two nonmetals, right? And so these guys over here on the right. Now the reason that that rule of thumb works is that if you have two nonmetals, they both typically have relatively high electronegativities. The difference between those electronegativities is going to be relatively small. So you might have a nonpolar or a polar covalent, but it's still a covalent bond. It's still a sharing of electrons. So the next thing we need to worry about would actually be the overall polarity of molecules. So I've mentioned that you can have a polar covalent bond, right, in which case the electrons are getting pulled to one side or the other. But what about the overall molecule? So let's take a look at carbon dioxide again. So looking at the electronegativity values for carbon and oxygen, you can clearly see that carbon is less electronegative than oxygen. So you can think of the oxygen as pulling those electrons to the right. But what about the oxygen on the left? Well, turns out that that oxygen's very electronegative and pulls those electrons to the left, right? Which means that overall, the two dipoles cancel each other out. And so even though we have what are known as polar covalent bonds, which are unequal sharings, so polar covalent bonds, we actually have a nonpolar molecule, okay, because the dipoles actually canceled each other out. So let me tell you a quick story that is how I always remember this, okay? So my very first chemistry teacher back in high school told this story, and she swears that it's true. So she had this dog, right? And the dog had 5 puppies. And the 5 puppies were very cute and adorable. She also had this big mean tomcat, and the tomcat would sit on the porch swing, and every morning the puppies would come running out through the little doggy door, and the tomcat would take a swipe at each one with its claws. The puppy would go yelping and running off, and the tomcat would just sit there. And this kept happening day after day, day after day. And then one day my chemistry teacher came home and she heard this horrible screeching sound. And there, on the porch, was the cat. Okay, you can see my horrible art skills again. And the cat is not happy because one puppy has grabbed onto each one of its paws, and one puppy has grabbed onto its tail, and they're all pulling in opposite directions, right? So where's the cat going? Well, absolutely nowhere. And so after she stopped laughing, she saved the cat, and the cat never swatted a puppy again. So lesson learned. So this is how I always remember, polarity of molecules, is even though each of these is getting pulled in a direction overall, the molecule is what we consider a nonpolar molecule. Now, there are some molecules that are polar because there's not this equalizing force, right? So let me give you an example here with water. All right, in the case of water, oxygen's much more electronegative and so it's pulling the electrons in each of these bonds. You can see that they're kind of both pointing up, but there's nothing up here. There are just these lone pairs. There's nothing that's kind of going the opposite direction. And so overall, the dipole would head this way, right? So overall, we have one side of the molecule that has a slight negative charge and one side of the molecule that has a slight positive charge. And this would be an overall polar molecule. Let's go ahead and practice this, and we'll see if we can figure out which of the following molecules are polar and which are nonpolar. Now, honestly, the easiest way to do this, some people prefer to actually draw out the dipoles and try to kind of look at like a physics method. I do something a little simpler, maybe because I'm a simple person, but I like to play one of these things is not like the other. Remember that from Sesame Street? So if I'm looking at this molecule over here on the left, this methane molecule, all right, I look around that central atom, that central carbon. It has 1, 2, 3, 4 things around it, and they are all exactly identical, right? So in that case, since they're all identical, this would be a nonpolar molecule. Easy as that. Now, what about this molecule here in the center? All right, well, in this case, we have 4 things around that carbon. 3 of them are hydrogens, and 1 of them is a fluorine. Okay, one of these things is not like the other. Therefore, this has to be a polar molecule. Okay, it's kind of lopsided. All right, what about this last one over here on the right, the ammonia molecule? Well, notice that there are 4 things around here. 3 of them are hydrogens, and 1 of them is a lone pair. So yes, we do have to take into account the lone pairs. And so this is also a polar molecule because one of those things is different, right? So if at least one thing is different, then you have a polar molecule. Otherwise, it's nonpolar. Now, don't let me fool you, because I could draw it like this, right? I could draw a water molecule that makes it look like it's a nice linear molecule. And so you might be tempted to think, oh yeah, see, they're on opposite sides, and so they end up canceling each other out. But they don't, because you have to think in 3 dimensions. So in this case, what I would do is I'd simply look at that central oxygen and say, you know what, this has 1, 2, 3, 4 things around it. 2 of them are hydrogens, and 2 of them are lone pairs. They're not all the same. You know, at least one of these things is not like the other. Therefore, this is a polar molecule. And you might be thinking to yourself, why in the world do I care, right? Why does this matter at all? It seems silly to go through all the effort of drawing these molecules just to figure out whether they have polar bonds and whether they're polar molecules and so forth. Well, the reason for this is because so many of the properties are determined by the polarity of the molecule. So there's a rule of thumb in chemistry that says that like dissolves like. Okay, pretty important rule. What that means is that polar molecules like to dissolve in other polar molecules. Nonpolar molecules dissolve in nonpolar molecules, but nonpolar and polar do not mix. So, for instance, ammonia is a polar molecule. It dissolves very nicely in water because water is a very polar molecule, so they dissolve easily in each other. But water and vegetable oil don't mix, or vinegar and vegetable oil, right? So when you try to make salad dressing, you end up, having a separate layer of vinegar and vegetable oil no matter how much you shake it, because vegetable oil is very nonpolar and water or vinegar is very polar, and so they end up separating. Now, if you really, really wanted salad dressing that didn't separate, you could use vegetable oil and gasoline, because those are both nonpolar, and so by putting those together, they would mix very nicely, and then people would stop coming over for dinner all the time. Okay, now this also applies to if you like to work on cars. If you get a bunch of grease on your hands, grease is very nonpolar, which means if you try to rinse it off with water, it doesn't work because water is polar. Like dissolves like, so they don't dissolve in each other. But you could go ahead and take some gasoline and pour that over your hands, and the gasoline will dissolve the grease and take it right off. Just don't try to light a cigarette after that, because your head would explode. So just use it responsibly. All right, so that wraps it up for drawing molecules, kind of a visual thing. Hope you've been able to follow along, and I'll see you next time.